Okay, let me go to the next topic, which how we address this physics issue, and for that we need detector, and my talk will be focusing on the detector, how we are going to build and what are the difficulties, what we are going to get out of this detector. So this is my outline. First is I will talk about the neutrino detection. This is very important, and then just to touch base on particle detectors, then see what our detector is called ICAL, iron calorimeter, where we stand, how we are going to build this, and I will conclude my presentation. In dedicated neutrino experiment, it is very difficult to detect neutrino as mentioned by previous speaker, because it interacts very weakly with matter. So if you want to detect neutrino, you have to have large amount of interacting material which is called mass. For ICAL we have iron as the catalyst. So with iron we can detect neutrino indirectly. I will talk about how. In accelerator experiment, like you have heard about Higgs boson, all other experiment, why don't they do this measurement, and why do we need a dedicated facility like INO? Because if you go to electron-positron collider, which led to Nobel Prize in CP violation, they also produce neutrino, but they cannot, because in their experiment all the three momentum of the particle has to conserve. If you go to proton-proton collider, which discovered Higgs boson, they also produce neutrino, but they cannot detect neutrino. So there is a limitation that if you want to study neutrino properties, you have to have dedicated experiment like INO. Why do we need the detector? Detectors allow us to detect particles. Experimentally study their behavior, this particles behavior, and new particles are found by direct or indirect, or through their decay you can detect the new particles, or you can study the properties of known particles like neutrino. Theorists predict the properties, experimentalists design the particle detectors and build the detector. What do we do? Measure using this detector. What exactly we do with this detector? We want to know the location, the path where the particle has gone is called spatial location in ICAL. The trajectory, if you have, that's not enough. To do the measurement, you need the magnetic field which will help you to measure the momentum and the charge of the particle. You can also measure the production point where the particle has been produced, and when it decays, that will allow you to measure the lifetime of the particle. You can also measure the energy. This is in ICAL, we do want to measure the energy. There we have the relation momentum plus energy gives you mass. Okay. This is just one slide to tell you that all the collider experiment, they have multiple number of, means very different detector together make one detector. If I talk about Atlas or CMS, you have many detector. You have a tracking detector which measure the trajectory, you have electromagnetic calorimeter, measures the energy of photons, electrons, you have hadron calorimeter which measures the energy of hadron, and you have muon detector which measures the muon. You see, you need 4 different detectors to do the experiment. If you look at the left hand side, it shows you photons, electron, muon, pion, everything you detect, but nothing is about neutrino. So the question is, this detection of neutrino is a challenge actually, and you have to be very patient to do this kind of experiment. How do I going to measure this detector? build the detector and do the measurement. The first thing is direct detection of neutrino is impossible as mentioned by our previous speaker because it's a weak interacting particle. Okay. So because it's a cross section, the interaction cross section is very small. Just for example, if you think a few MeV neutrino you want to have interaction, one you need like 10 light years of thickness of steel plate. This is what you think. So this is a challenge actually, and once the theorist, which Wilbur Powell, made a statement, I have done something very bad today when he proposed this by proposing a particle that cannot be detected. It is something no theorist should do ever. But now we are detecting neutrinos, with the things have improved. How ICAL is going to detect neutrino? Neutrinos are detected through their interaction with nucleons. In case of ICAL, with the iron provides this nucleons, resulting the new particles, which is muon and pion. Basically, when neutrino comes, interact with the nucleons, you get muon and pion. That tells you that neutrino has interacted. Through the detection of muon and pion, you can do everything about the neutrino which has produced this. This is like indirect way. So in our case, it is important to measure muon and pion. So ICAL detects muon and pions. Finally, we get the energy and direction that will give us the neutrinos energy that is used for all the physical measurement which the previous speaker talked about. So in case of detector, what we do basically, we measure the momentum and energy direction, put into the formula given by theorist and do the final product. Okay. What are the challenges for ICAL? Is it so easy or is it difficult? We will see. The special thing about ICAL, as mentioned by previous speaker, that this has the capability to differentiate between neutrino and antineutrino by detecting positive and negative muons. It does not say muon, it will tell you whether it is a positive muon or negative muon. That will tell you whether it was produced by neutrino or antineutrino. This picture has been shown many times. So this is 50 kiloton which is proposed for the ICAL detector. We do not build 50 kiloton at a time, we have to see the granular way. What is the smallest building block of this 50 kiloton detector? The smallest building block is called this RPC, and this RPC is 2 meter by 2 meter glass. So smallest building block is 2 meter by 2 meter glass RPC, and we use 30,000 of this to make this gigantic detector. Then what I mentioned, actually we also want to measure the muon and anti-muon or mu plus and mu minus. For that we have to magnetize this big gigantic detector, and it has never been done in the world to make the so big electromagnet. So this is a challenge for engineering purpose also. It's never been done in the world, and we are going to do the first. What do you see in the detector? Once you see the detector, this is the detector volume. Once neutrino comes, it interacts, and it gives you two types of hits. The first one is muon, which gives you a trajectory where you can measure the momentum. But in case of red color one is called hadron, is pion, is a strong interacting particle. It gives you a bunch of hits because it's a strong interacting particle. It loses all the energy quickly. So challenge is to separate this hadron and muon. Make sure that you separate them, otherwise you mix, then you will not get the proper measurement. That's a challenge for us. If you remember my previous slide, all the experiment uses the particular detector for measuring particular particle. In case of ICAL, we are using one detector to detect muon and hadron. This is a challenge. How do we do that? though we don't make this 50 kiloton ICAL in few years also. First you start with a very small detector in your lab, which is called R&D, which has started 15 years back, before we go to the big detector. I will go through this small piece which basically gives a proof of principle how you go for 2 meter by 2 meter RPC and make 30,000. First you can be in the lab, you don't need to do 2 meter by 2 meter, you can give the 1 feet by 1 feet glass and make this gap. So glass is bad conductor. So what you do actually, you make a coating to make it conductor. So you make 2 glass plate and put together with 2 mm gap, and if you see this gas gap is, the gap is there because we need to provide the gas which will use for ionization when the particle pass through the detector. And once you make the gas gap, you can put together, and this is what is called RPC. You have the wires, this is called one channel. You read out whenever have any signal, okay. This is the gas composition we have to use. We have to use this gas composition, and this is the circuit. So you have gas supply and it goes to RPC and then goes to the atmosphere in the lab. But if you could talk about ICAL, it is very difficult to waste this gas. So we do the recycling, so we reuse this gas. This is the lab setup. Once you measure and make the setup that what type of detector you want to build in your lab, you go for the industrial production, that means you are ready to produce 2 meter by 2 meter. And this is one of the lab industry in Chennai which is making this RPC. Now it's at industrial production. We are making 400 of this. How do you know that this gas gap or RPC is working? First thing, you apply high voltage and you see it will pick up the current, and this left hand side plot shows you that it is responding your high voltage. You look at the number of parameter, one of them is the timing, is good enough. You look at the efficiency, is very important. You see our detector is more than 95%, and this is the small scale. And if you talk about ICAL, which is composed of 30,000 of this 2 meter by 2 meter, we do not have that detector yet, but we can do the simulation. And in the simulation, you see that depending on the angle, you see the efficiency varies, but mostly it is more than 95% for mu1. And as I mentioned that we have the capability to measure the charge, and the right hand side plot shows the charge identification, which is more than 97%. Times we can tell whether it is a mu plus or mu minus. With this, we move to the other one, which I said is a hadron. It is very tough because we are not designed to measure the energy. What we see actually, it gives the blob of cluster of hits actually, and we can we use this hit to measure the energy of hadron? Yes. You look at the hit and see that how the true hit looks like is a simulation, and if you have a noise, how it looks like, and you can parameterize the number of hit you get in the detector as a function of incident charged particles momentum or energy. And from there you do the calibration, use this calibration to get the real energy of the particle. It is a tough job. This is what we do, and you see x axis is the energy, y axis is the number of hit. From hit information we are getting the energy. This is not directly getting the energy like in Hadron Collider. So what do you do? Is it so simple? No. You can further analyze the heat distribution and look at the shape of the distribution, and then you get the more improvement using your advanced algorithm, and it shows you how it looks like. It's improved. So we are working hard on getting better and better energy resolution, reconstruction energy through the improved algorithm. Conclusion: neutrino detection is challenging. if the source is nature, because source does not change the number of neutrinos produced today and tomorrow is constant. You are in the God's hand actually. If you use accelerator, you can control the production rate. So we are using atmospheric neutrino. All R&Ds have been done in India. This is made in India. ICAL is ready for production. Last 15 years of hard work on R&D now is fully complete and we are in the production stage. We are ready to do the even 30,000. INO experiment is designed to make a good impact in this field of research. As mentioned, this is the only detector having the capability to differentiate muon and anti-muon, that is neutrino and anti-neutrino. Good opportunity for student to pursue research in the as a career also, because it is a mega science project and that will open up next 50 years of research. So this research will put India in global map and we hope that we get the success in this research. Thank you.